Electrolysis involves splitting water into hydrogen and oxygen with the help of electricity. When a direct current is passed through the water, oxygen disappears from positive anodes, while hydrogen is released from the negative cathodes. In terms of volume, exactly 2 times more hydrogen is produced than oxygen. As pure water is not a good conductor of electricity, something like salt is added, not a very environmentally sound method. If you use a proton exchange membrane, PEM for short, it's possible to extract hydrogen from pure water, as the membrane provides the necessary particle transport between anodes and cathodes.
Anyway, you can see that later on. We're going to the tour now. Okay.
This is hydrogen gas in the Kangen water 9.5. You can see a lot of bubbles.
In this video, we're going to focus on the electrolysis of water. So what exactly is electrolysis? It's the process by which we use electricity to break down a compound into its component molecules. An example of water, we can use electricity to break down this compound into hydrogen gas and oxygen gas. Now let's talk about how we can actually do this. A quick and simple way is to take a beaker, fill it with water, and we need to use 2 electrodes. One of them is going to be the anode and one will be the cathode. Now I'm going to use 2 carbon-based graphite electrodes, and I'm going to connect a battery to it. So the long side is the positive terminal of the battery, and the short side is the negative terminal of the battery. I'm going to use a 9-volt battery. And so we're going to add water, and I'm going to dissolve sodium hydroxide into the solution. So what's going to happen once I connect the battery? Electrons will flow towards the positive terminal of the battery and away from the negative terminal of the battery. Now, in an electrochemical cell, electrons flow from the anode to the cathode, which means that the electrode on the right represents the anode, and the electrode on the left represents the cathode. Now, you need to know that oxidation always occurs at the anode, and reduction always occurs at the cathode. So what is the oxidation half reaction that occurs at the anode? At the anode, hydroxide is oxidized into water and oxygen gas, and it's going to give off 4 electrons in this process. Well, technically it's oxidized to oxygen gas, but water is a byproduct of that half reaction. Now at the cathode, water is reduced to hydrogen. So it's going to pick up some electrons and it's going to turn into hydrogen gas, and it's going to generate hydroxide ions. So let me put a line to separate these 2 half reactions. So at the anode, you have the evolution of oxygen gas. Oxygen gas is going to come out of the anode. And at the cathode, hydrogen gas will be produced. And so that's the basic setup of an electrochemical cell. So if you add electricity to an aqueous solution of sodium hydroxide, you're going to get hydrogen gas at the cathode, which is the electrode attached to the negative terminal of the battery, and you're going to get oxygen gas at the anode, which is the electrode attached to the positive terminal of the battery. Now let's talk about what happens in between. So these are the two electrodes that we were talking about earlier, and we have a battery attached to it. Now the anode is attached to the positive terminal of the battery, so therefore it's going to have a positive charge on it. And the cathode is attached to the negative terminal of the battery. So there's going to be an electric field that flows from the positive plate to the negative electrode, or the negative plate. Now inside an electric field, a positive charge will feel a force that will accelerate it in the direction of the electric field. A negative charge will feel a force that will accelerate it opposite to the direction of the electric field. So the sodium ions, they carry a positive charge, and so they will feel a force that will accelerate them towards the negatively charged plate, or the cathode, since the cathode bears a negative charge. The hydroxide ions will feel a force that will accelerate them towards the positively charged anode. Now, once the hydroxide ions make contact with the anode, they will give up their electrons, causing the electrons to flow in the circuit. And as a result, the hydroxide ions are oxidized into oxygen gas as they give up those electrons. And what was the reaction that I wrote before? It was O2 plus 2H2O plus 4 electrons. Now, sodium is not going to be reduced at the cathode. And let's talk about why. If sodium picks up an electron and turns into sodium metal, the cell potential for this process is not favorable. It's a negative 2.71. Whereas if water picks up the electrons and is reduced to hydrogen gas, the cell potential is only negative 0.83. So comparing these two values, we could see that it's a lot easier to reduce water at the cathode than sodium at the cathode. So for the most part, this reaction doesn't happen. And if by some miracle it did happen, notice what's going to happen. So let's say if some sodium metal was actually reduced in the cathode, sodium will immediately react with water to create hydrogen gas and sodium hydroxide. Because it's known that if you put sodium in water, it reacts. It basically explodes in water. And so hydrogen gas will be produced. So therefore, even if sodium did form, it would immediately react with the water molecules surrounding it, turning back into the sodium plus anion. I mean, not anion, but sodium plus cation. So because this cell potential is highly unfavorable, it's not going to form on the cathode. And if it did, it's immediately going to go back into the Na plus state, because that state is a lot more stable. Now water, in this case, is going to be oriented in this direction. The oxygen part of water bears a partial negative charge, and the hydrogen, I need to put a 2 in front of it. Let me redraw that. The hydrogen bears a partial positive charge. So notice that the hydrogen of water faces the cathode. The oxygen faces the anode. The oxygen is attracted to the anode because they're oppositely charged, and the partial positive charge of the hydrogen is attracted to the negatively charged cathode. And so the water molecules that are close to the cathode, they can easily be reduced into hydrogen gas. Those water molecules can pick up the electrons, and some of it will turn to hydrogen, and hydroxide will be produced. Now let's go back to this reaction. Now let's understand how sodium reacts with water if by some miracle is produced at the cathode. So immediately, sodium will give up its electrons to turn into this ion. And then water is going to pick up those electrons and be reduced to hydrogen gas and hydroxide. So if we combine these two reactions, we could cancel the electrons, and so we're going to get on the left side sodium, water, hydrogen gas, and we can combine these two into sodium hydroxide. So that's why sodium will not form at the cathode. If it did, it's going to immediately react with water, producing this stuff. Now let's put it together. So at the anode, where oxidation occurs, this is the half reaction that we have. So we said that hydroxide is going to be oxidized into oxygen gas, and water is going to be a byproduct of this reaction. And the cell potential for this is negative 0.4 volts. Now, reduction is going to occur at the cathode. And so at the cathode, water is going to be reduced. Now I'm going to multiply that reaction by 2, so it's going to be 4 H2O molecules, and it's going to pick up 4 electrons to produce 2 hydrogen gas molecules and 4 hydroxide ions. And so the cell potential for this is negative 0.83 volts. Let me write that better. Now let's add these two reactions. Now you need to make sure that the number of electrons are equal, so that when you add them, they cancel. Notice that the hydroxide ions cancel as well. And so we have 4 water molecules on the left, 2 on the right. So if we subtract both sides by 2 H2O molecules, this will disappear, and this will be reduced to 4 minus 2, which is 2 H2O. So on the left side we have 2 water molecules, and on the right side we have an oxygen gas molecule and 2 hydrogen gas molecules. And the overall cell potential for this, when we have a 1 molar sodium hydroxide solution, so that's the standard concentration. If you change the concentration, the cell potentials will change. But at a standard concentration of 1 molar sodium hydroxide, it's going to be negative 0.4 and negative 0.83 together. If you add those two, the cell potential is negative 1.23. So this is the minimum voltage that you need to drive this reaction forward. Now, as you can see, the cell potential is negative. So this process is non-spontaneous the way it's written, which means that water doesn't naturally just... I gotta fix something. This is supposed to be 2 hydrogen gas molecules, not 2 H2O molecules. So water doesn't naturally decompose into oxygen and hydrogen. You gotta put energy in order to break it down into those component elements. So water is very stable. And so that's electrolysis, the process of using electrochemical energy, or electric energy rather, to decompose water into its component elements. Now the reverse reaction is spontaneous. So hydrogen gas mixed with oxygen gas will decompose, or rather will react to form water. And the cell potential for that is going to be positive 1.23 as opposed to negative 1.23. So this will happen spontaneously. Now you may need a spark to speed up the reaction to get it started. So even though this reaction is thermodynamically favored, it's not very fast unless you increase its temperature or ignite it with a spark. It can still happen, but it happens slowly without meeting the activation energy needed to get this reaction started. So that's it for this video. Thanks for watching, and have a good day.